Okay, so last time we ended up getting some Reynolds averaged equations, and this is what we ended up with when we Reynolds averaged the when we Reynolds averaged the momentum equation. So if we just look at this for a little bit, we have pretty much all the terms that we had before we Reynolds averaged it, plus this additional term related to turbulent mixing, and that's called the Reynolds stress, right? And I guess if you want to come over here and focus on this side of the equation, what we've really done is we've taken our viscous stress, which is momentum transfer due to molecular diffusion, and we have augmented it with this Reynolds stress, which is momentum transfer due to turbulent mixing, okay? And that's related to this integration of the fluctuations in U multiplied by the fluctuations in V, right? And we said that's because, these fluctuations in V are really what takes big packets of fluid with either lower or higher x momentum and moves it away from the wall, right? So that's the process that's going on to cause momentum transfer in this turbulent mixing. So the first thing, what we're going to do today is express this second term in terms of what's called the Eddy diffusivity, right? So for this momentum equation, this will be expressed in terms of the Eddy diffusivity of momentum. If we're going to talk about the energy equation, it'll be the Eddy diffusivity of heat transfer, but it's basically going to make this term look a lot like the viscous term, right? And we'll have this basically turbulent viscosity or turbulent kinematic viscosity, and we'll have a turbulent conductivity or a turbulent thermal diffusivity. And so the first thing we have to recognize is that this term that we're familiar with is related to the gradient in the U velocity, right? We have viscosity, and then we know that momentum transport by molecular diffusion is driven by gradients in velocity, just like energy transfer by molecular diffusion is driven by gradients in temperature, right? So this term, this turbulent term, doesn't seem to be driven by gradients in velocity, but actually it is, right? And the reason is because, if we go back to why it is that these two quantities, when multiplied together, don't integrate to zero, the reason that is because they're correlated with each other, right? So we talked about how when we have a velocity distribution like we have here, right? If I have a positive y velocity fluctuation, what that means is I'm going to take a big hunk of fluid that has a relatively low u velocity, and I'm going to move it out into a region of the flow where the u velocity is higher, and that's going to initiate a negative fluctuation in u. So these two things are related to one another, right? But that relationship depends on there being a velocity gradient, right? So this is velocity as a function of distance from the wall. In this region here where I have a positive velocity gradient, I would expect there to be a negative correlation between these two things. But if we move out into a region of the flow where there is no velocity gradient at all, then if I have a positive fluctuation, the y velocity, I'm taking some fluid with a certain u velocity and I'm moving it out into a region of the flow that has the same u velocity. So I would not expect then to have any u velocity fluctuation induced at that point, right? So the point, I guess, is that this correlation that I get here is proportional to the magnitude of the velocity gradient. So this Reynolds stress term here is proportional is proportional to du dy, right? So just like the molecular diffusion is proportional to du dy, and the constant of proportionality, we call that the viscosity, the Reynolds stress is also proportional to du dy, and we're going to call the constant of proportionality rho, the density of the fluid, times epsilon sub m, where epsilon sub m is the Eddy diffusivity of momentum, right? So what I've basically done is I've taken this term here, that is the Reynolds stress, and I've expressed it in terms of something that looks a lot like the viscous stress due to molecular diffusion, right? Instead of having a viscosity here, I have something that's related to the eddy diffusivity of momentum, right? And I understand why it is that this term should be proportional to du dy. I've just defined then the constant of proportionality to be rho times epsilon sub m. So this is the quantity then that we need to model, right? We understand what it's modeling, but we need a model of this turbulent viscosity. And if we start to think about kind of what the analogs are here, let's see. I have viscous stress, right? It has a molecular viscosity. If I go over here, I have now a turbulent stress, a Reynolds stress, and it's got a turbulent viscosity, which is rho times epsilon sub m. These two quantities play the same role, right? They just they have the same units. They just represent different aspects of the momentum transport process. If I divide viscosity, molecular viscosity by density, I get kinematic viscosity. Right? If I divide our turbulent viscosity by density, I get the turbulent kinematic viscosity, which is just the eddy diffusivity of momentum. So the eddy diffusivity of momentum, you can think of it as the turbulent equivalent of kinematic viscosity, right? And I can take now my equation and express it in terms of this last term. I can express it in terms of an apparent stress, which is the sum of the viscous stress and the turbulent mixing stress, or the Reynolds stress, right? And basically, that's just by adding these two viscosities together. You know, I would expect that there will be, so just to be clear, everywhere in the flow, there is this molecular viscosity. It never goes away. But what happens is, in regions of the flow where the turbulent eddies are present and active, this term here, this turbulent viscosity, is going to be much, much bigger than this term here, right? So as I move away from the wall and I go through the viscous sublayer, in the viscous sublayer, there are no turbulent eddies. I would expect that I would only have this molecular viscosity, right? But as I move through the viscous sublayer, through the transition region, and then into the turbulent core, I would expect this term to grow and grow and grow and eventually dominate the molecular viscosity. All right, so we can do the same thing then with the energy equation, right? So we have here the Reynolds average energy equation. Right, so this is the whole thing. Again, you know, if you look at it, most, what is it, like 80% of it looks familiar, and we're left with this one term that came out of the Reynolds averaging and wasn't equal to zero, right? And so over here on the right side, we have energy transport by molecular diffusion. That's this guy here. This is Fourier's law. We've been talking about this from day one. This is the additional term that we have that represents the action of turbulent mixing. And, you know, again, we have this V prime term here, which is driving that turbulent mixing, right? These fluctuations in V velocity are really taking flow and moving it quickly and efficiently from near the wall towards the away from the wall, right? And so anytime you have a V prime, a fluctuation in that V velocity, you're going to likely get a T prime, a fluctuation in the temperature, right? But we can make the same kind of argument here, which is that the reason these don't integrate to zero is because they are correlated, but the only time they'll be correlated is when there's a temperature gradient, right? So here, you know, our molecular conduction term or our diffusion term, or molecular diffusion term, is obviously related to the temperature gradient, right? This guy here, this turbulent term, it also should be related to the temperature gradient, right? And so to see that, you know, we can sort of do the same kind of mental exercise, right? Here is a temperature distribution, right? This is distance from the wall. This is temperature, average temperature of the flow. If I'm down here close to the wall where I have a pretty strong negative temperature gradient, right? Temperature's dropping in the y direction. If I get a positive y velocity fluctuation, physically what that's going to do is take a hunk of relatively hot fluid and throw it out farther from the wall where the fluid is relatively colder. So that's going to induce then a positive temperature fluctuation, right? So these two things would be positively correlated to one another when I have a negative temperature distribution, right? A negative temperature gradient, sorry. If I move out here farther from the wall where the temperature gradient goes away, then a positive V velocity fluctuation is going to take fluid that has some temperature and move it out into fluid that has the same temperature. There's going to be no temperature fluctuation induced by that activity, right? So, you know, the correlation of V prime with T prime is going to go away. It's not, just to be clear, it's not that these quantities stop fluctuating. They still fluctuate just as much, right? What happens is those fluctuations become decoupled from one another. There's no correlation anymore. When you have a V prime, you're not any more or less likely to have a T prime that goes along with that when you're out here in the region of the flow where there's no temperature gradient, okay? So the outcome of that is that the energy transport due to turbulent mixing is also related to minus dt dy, just like the energy transport due to molecular diffusion was related to minus dt dy. So, you know, again, you know, we have here a molecular conductivity. What we're going to do is have a turbulent conductivity, and we're going to express that turbulent conductivity as rho times C. So this is the density and the specific heat capacity of the fluid multiplied by the eddy diffusivity of heat transfer, epsilon sub h. So we have the eddy diffusivity of momentum. That helps us define a turbulent viscosity. We have an eddy diffusivity of heat transfer. That helps us define a turbulent conductivity, right? So that's what this is right here. So we can go through again what the analogs are here between the turbulent and the molecular quantities, right? So we have molecular conductivity. Over here we have a turbulent conductivity, which is rho times C times epsilon sub h. This has units of watts per meter Kelvin. This is a state variable, right? If I know the state of the fluid, I know its temperature and pressure, I can go look up what the molecular conductivity is. It's a property. Turbulent conductivity has units of watts per meter Kelvin, right? But it is not a property. If you tell me the temperature and the pressure of the fluid, that doesn't get me any closer to telling you what the turbulent conductivity is, right? This is related to a whole bunch of things about the flow and the flow conditions and the velocity and all that kind of stuff. If I divide the molecular conductivity by rho times C, I get the thermal diffusivity, right? Again, another property that tells us about the molecular energy carriers. If I divide the turbulent conductivity by rho times C, I get epsilon sub h. So you can think of this eddy diffusivity of heat transfer as being the turbulent equivalent of thermal diffusivity, right? And so I can take this last term here, which is the diffusion of energy related to both molecular diffusion and turbulent diffusion. I can take that last term and I can express it as an apparent heat flux, right? So it's the sum of the molecular diffusion and the turbulent mixing. And basically all I'm doing here is adding those two conductivities together to get me a total conductivity of the fluid. So just like we talked about with viscosity, when I'm in a region of the fluid where there are no turbulent eddies, this term would disappear, this turbulent conductivity, and I would be left only with the molecular conductivity. So, for example, in the laminar part of the boundary layer, I would be left only with K here, and actually this entire equation would just limit back to our boundary layer equation, right? But if I move into a region of the flow where turbulence is present, then this term starts to become active. This term, the conductivity, the molecular conductivity, does not go away. It's still there. It just becomes really, really small compared to this term, and the turbulent conductivity dominates the problem, right? So here's just kind of another complete list of the analogues, molecular quantities that we're sort of used to from laminar flow, and their turbulent quantities over here. So viscosity and turbulent viscosity, kinematic viscosity, epsilon diffusivity, the eddy diffusivity momentum, molecular conductivity, turbulent conductivity, molecular thermal diffusivity, and the eddy diffusivity of heat transfer. And actually, if you want to go one more step, if I take the molecular kinematic viscosity and divide it by the molecular thermal diffusivity, I get the molecular Prandtl number, right? If I take the turbulent equivalent of the kinematic viscosity and divide it by the turbulent equivalent of the thermal diffusivity, so epsilon sub m over epsilon sub h, I get the turbulent Prandtl number, right? And it's kind of interesting to think about. Over here, we said the molecular Prandtl number is a quantity that reflects how well a fluid does at transporting momentum relative to energy, right? If we have a liquid metal, for example, liquid metals are really good at transferring energy, not so great at transferring momentum. We would expect a molecular Prandtl number that's kind of a lot different than 1, and actually a lot less than 1. Right? Oil is the opposite kind of a thing, right? You have these long chain molecules. They're really good at transferring momentum. It's not helping you that much with energy. We would expect Prandtl numbers much greater than 1, right? So molecular Prandtl numbers can be very different than 1 if the mechanisms for transporting momentum and energy are different in the fluid. On the other hand, a turbulent Prandtl number, we're talking about transporting momentum via turbulent eddies, and we're talking about transporting energy via turbulent eddies. So the mechanism on the top and the bottom here, they're going to be exactly the same for any fluid, right? And so as a result, you would really never expect to have a turbulent Prandtl number that's very different than 1. And in fact, the turbulent Prandtl number is always very close to something like 0.9. Right, so even if you have a liquid metal or some weird fluid, or not even weird, some fluid where the Prandtl number, the molecular Prandtl number is quite a bit different than 1, the turbulent Prandtl number that characterizes the ability of the fluid to turbulently transport momentum to energy, that turbulent Prandtl number will still be very close to 1. All right, so just looking ahead now to finish up turbulence over the next couple of lectures. What we want to do is derive the law of the wall, because I think it's important that you all know what that means and where it comes from. It's just a really handy thing to understand if you're a thermal fluids engineer. So when we derive the law of the wall, what we're really going to do are a few things. First of all, we're going to have to come up with models for this turbulent viscosity here, and for the turbulent conductivity as well. And there's a bunch of models for these things, right? This is 4 out of umpteen billion, right? So these are 4 relatively simple ones that we can use, but there's just page after page of these if you open the right book, right? But one thing you'll notice is that these models for, in this case, the eddy diffusivity of momentum, are written in terms of, over here you see y plus, and down here you might see u plus, and in some cases you might even see theta plus, right? Those are inner coordinates. This is y plus, this is a dimensionless position relative to the wall, and it's made dimensionless based on basically trying to come up with a scale for the viscous sublayer, right? And this u plus is a dimensionless velocity made dimensionless based on the scale of the fluctuating component of velocity, and theta plus, the same thing. It's a dimensionless temperature, but it's made dimensionless based on normalizing by the scale of the temperature fluctuation. So the point there is that y plus, u plus, and theta plus are things we have to understand. And the other point there is that these inner coordinates, which are important for turbulent flow, are made dimensionless based on the quantities that are important for a turbulent flow. Right? We're not going to normalize y by the boundary layer thickness, because the boundary layer thickness in the turbulent flow isn't very important. What's important in the turbulent flow? The viscous sublayer thickness. So that's what we'll use here. Same thing here, u plus. We're not going to normalize u by the free stream velocity, because that's not the important velocity relative to transporting momentum. We're going to normalize it by the magnitude of these fluctuations that are so important, right? And the same thing for temperature. So one thing we'll need to understand is the inner coordinates, and how they're defined, right? And how we use them. Once we've understood that, then we have this model, so we can plug into here and at least come up with a math problem that we can solve, right? The last thing we'll do before we actually try to solve it is we'll actually restrict ourselves to a region very close to the wall, much bigger than the viscous sublayer, but much smaller than the entire boundary layer. So close enough to the wall where what's called the Couette assumption holds. And the Couette assumption basically says all these terms are negligibly small except for this last term right here. So in the Couette flow region, the apparent shear stress is the only term that we'll retain in this entire equation. So that's where we get the law of the wall from. And it's only valid in the Couette flow region for some specific model of the turbulent viscosity or the turbulent conductivity. All right, so that's what you have to look forward to in the next couple of lectures.